Okay, so we're going to talk about carboxylic acids, and this is important because it ties to what we've been studying for aldehydes and ketones. And we care a lot about carboxylic acids for a couple of reasons. So when we think about the functional group of carboxylic acids, we can represent them several different ways. And the reason we represent them several different ways is because they're found in a variety of different compounds. And so sometimes we can convey information depending upon the way we represent that carboxylic acid. The formula of an aliphatic carboxylic acid is RCOOH. The formula of an aromatic carboxylic acid will be ARCOOH. And that's going to be important because when we think about IUPAC names, we're going to drop the E from the parent alkane. We're going to add the suffix oic acid. So if the compound contains a carbon-carbon double bond, then we can change that infix from AN to EN. So for example, if we take a look at each of these three molecules, how could we name them? Different representations. Take a pause if you need to. There are other ways that we can think about naming compounds. So remember, the carboxyl group takes precedence over almost any other functional group. So that means carboxylic acids are always going to be number one when we're numbering or naming compounds. So for example, 5-hydroxyhexanoic acid, 4-aminobutanoic acid, or 5-oxohexanoic acid are all examples of compounds where the carboxylic acid takes precedence and then the other functional group is named based on the numbering of the carboxylic acid. It's also pretty common for us to see dicarboxylic acids. So we're going to add dioic acid to the name of the parent alkane containing both carboxyl groups. So for example, oxalic acid, malonic acid, succinic acid are all examples of very common metabolites. And so these we're going to name using the IUPAC system as well, but in this case it's going to be ethane dioic acid or propane dioic acid. And then if the carboxyl group is bonded to a ring, we're going to name the ring containing that compound and add the suffix carboxylic acid. So take a moment and think about how you would name these. Remember to pay attention to the stereochemistry. So 2-cyclohexene carboxylic acid, trans 1,3-cyclopentane dicarboxylic acid. The next thing that we're going to pay particular attention to is the way we look at carbons. So if we number carbon 1 as the carboxylic acid, then sometimes there's chemical reactivity that's associated with the carbons that are near that carboxylic acid. So we're going to label those as alpha, beta, gamma, and delta. So this is the 2, 3, 4, and 5 carbons. So for example, 4-aminobutanoic acid is gamma aminobutyric acid, or GABA, which is a very common chemical that we'll see in living organisms. And we'll talk about why being able to know the alpha, beta, gamma, delta designation is important in just a moment. So let's think about carboxylic acid. So in liquid and solid states, carboxylic acids are associated by hydrogen bonding into dimeric structures. And so it's important that we recognize the power of hydrogen bonding in these structures. They also can participate in terms of water solubility. So if I have amphoteric molecules that have a hydrophobic or nonpolar tail, and then a hydrophilic or polar head, such as decanoic acid, the carboxylic acid is often what makes the head of that molecule polar. When we think about carboxylic acids, these are going to be weak acids. They're not strong acids. So the values of pKa for most aliphatic and aromatic carboxylic acids fall within the range of 4 to 5. And so if we think about equilibrium, that means that the majority of those molecules stay as the acid instead of forming the conjugate base. So the greater acidity of carboxylic acids relative to alcohols, both of which contain an OH group, is due to the resonance stabilization of the carboxylate anion. We'll talk about that with some examples shortly. If we think about carboxylic acids and electron withdrawing substituents that could be on that molecule, so the more electron withdrawing substituents that are near the carboxyl group, that's going to increase the acidity through what we refer to as the inductive effect. So those are indicated here where we see a change in the pKa from 4.76 to 2.86 to 1.48 to 0.7 based on the number of chlorine atoms and the position of those chlorine atoms relative to the carboxylic acid. If we have a halogen substituent, the farther away that halogen substituent is, the less impact that it has. So if it's close, it has a significant impact. If it's far away, it has less of an impact. And we can see that by the decreasing acid strength as shown by the pKa. When we think about the reactivity of carboxylic acids, so whether they're soluble or insoluble in water, they're always going to react with sodium hydroxide or potassium hydroxide and other strong bases to give water-soluble salts. They also can react to form water-soluble salts with ammonia and amines. So think for a moment about how you would draw the reaction mechanism for these types of reactions. And then lithium aluminum hydride is what will reduce a carboxyl group to a primary alcohol. So this reduction is carried out in diethyl ether, THF, or other non-reactive or aprotic solvents. And then we also can do catalytic hydrogenation that is not going to produce a carboxylic acid group, but will reduce an alkene in the presence of that carboxylic acid group. Or if we wanted to, say, for example, selectively reduce a ketone in the presence of a carboxylic acid group, we could do that using sodium borohydride. So the next time when we talk, we're going to pick up talking more about carboxylic acids, but we're actually going to expand our conversation to include, so we're looking at esters and amides, as well as anhydrides and acid chlorides. And so we'll see you next time. Thanks again.